Welcome to Learn Chemistry Together. This video is about electrons, bonds, and Lewis structures. We are going to trace one of the most fascinating intellectual journeys in the history of chemistry, how we went from conceptualizing an invisible particle of charge to drawing the very bonds that hold our universe together. Our story begins in 1874, when George Johnstone Stoney of the National University of Ireland first proposed the existence of the electron. Attempting to explain electrochemistry, Stoney suggested that chemical phenomena were driven by discrete units of charge, and he coined the term electron to describe this hypothetical particle. 2 decades later, in 1897, J.J. Thomson at Cambridge University provided definitive experimental evidence using cathode ray tubes, measuring the charge-to-mass ratio, and cementing the discovery of the electron as subatomic reality. Yet, knowing that electrons exist is only half the battle. Chemists still needed to figure out how these particles dictated chemical reactions and molecular architecture. That breakthrough came in 1916 when Gilbert N. Lewis at the University of California, Berkeley, revolutionized our understanding by defining a covalent bond not as a mysterious force, but as the result of two atoms sharing a pair of electrons. To understand why atoms share electrons, we have to look at energy. When two isolated hydrogen atoms are far apart, their potential energy is defined as zero. But as they approach each other, powerful forces begin to interact. The nucleus of one attracts the electron of the other, while the nuclei repel each other and the electrons repel each other. At a very specific distance, 0.74 angstroms for a hydrogen molecule, a delicate balance is struck. This is the point of minimum potential energy, corresponding to a release of -436 kilojoules per mole of energy. Two separate hydrogen atoms possess higher energy. When they combine to form a stable covalent bond, H, energy is released, stabilizing the system. The potential energy well on a reaction coordinate diagram visually captures this. Internuclear distance impacts stability, and achieving that optimal 0.74 A bond length creates the lowest energy state for the H2 molecule. Armed with the concept of the electron pair bond, Gilbert Lewis devised a simple yet profound shorthand for visualizing molecules: Lewis structures. Lewis structures place electrons center stage, utilizing the atomic symbol as a core and surrounding it with valence electrons represented as dots. Constructing these structures relies on a few fundamental rules. 1. Valence representation. The number of Ts matches the atom's valence electrons. For atoms with 4 or fewer valence electrons like lithium, beryllium, boron, and carbon, each electron is initially drawn unpaired, sitting by itself on a side of the symbol. 2. Pairing up. For atoms with more than 4 valence electrons like nitrogen, oxygen, fluorine, and neon, the first 4 dots are placed singly and any remaining electrons are paired up with existing dots. The octet rule. Individual atomic dots combine to form molecules because atoms inherently tend to bond to achieve an electron configuration with a full valence shell, just like that of a noble gas. Whether it is a duet for hydrogen or an octet for oxygen and carbon, achieving this noble gas stability drives molecular geometry. Introduction to molecular formation. Combining atoms allows us to form stable molecules based on the noble gas configuration. The Lewis structures of individual atoms are combined to produce Lewis structures of small molecules, achieving a full valence shell. These drawings are constructed based on the observation that atoms tend to bond to achieve an electron configuration with a full valence shell, just like that of a noble gas. As seen with water, H2O, achieving a full valence shell involves an octet for oxygen and a duet for hydrogen to form a stable noble gas configuration, neon. By understanding how atoms share electron pairs to minimize energy and fill their valence shells, we unlock the foundational language of organic and inorganic chemistry. Thank you for watching, and please subscribe for more.